So module number 2 then is Missouri Department of Transportation's experience with SDCL steel bridge girder design. We're joined by Brian Hartnagel, who is the state bridge engineer for the Missouri Department of Transportation.
Okay, thank you, Kathy. I appreciate that. I'd like to thank Florida International University and their UTC for inviting us to talk about MoDOT's experience with SDCL girder designs. As she said, I'm Brian Hartnagel. I've been the state bridge engineer for the last more than 4 years and worked for MoDOT for over 23 years. Prior to that, I was a faculty member at Colorado State University for a little while and a graduate student at the University of Missouri at Columbia for a long time. So anyhow, I want to start off, I'm going to not start off with SDCL, but I'll tell you how we got there. So the topics in my presentation, we're going to talk about our national bridge inventory. We have the 7th largest amount of bridges. And I'm going to talk about our use and history of design build, because this is how we actually got to get SDCL bridges on our system, and why bridge bundling, and a summary of our previous bridge bundle project. And then the first application of SDCL was in the fixing access to rural Missouri. Every thing when you do a grant application, you've got to come up with a catchy acronym. And so we got a infogrant for this design build project, and I'll talk about the Farm Bridge project. And then since then, we've been doing additional simple for dead, continuous for live SDCL projects, and then I'll conclude with what's next for Missouri on this topic. So just to get in relation for everybody online, Missouri's in the center of the country. A lot of people think of us as flyover country. We are one of 2 states that border 8 other states, and we have some major rivers there, so we have a lot of bridges that we share with a lot of other states, including Nebraska, which you'll hear from later. So if we look at our March of 2025 NBI submittal, as you probably know, every state is required to submit their national bridge inventory to the Federal Highway Administration on a yearly basis, and this happens on March 15th. We like to do ours the Friday before March 15th, but anyhow, we have 10,427 bridges on our state system, and you can see that in the top left-hand corner. Now, a focus of our asset management approach over the last years has been reducing the number of poor condition bridges. And in the bottom left of the screen, you see poor condition bridges, and they are spread out pretty much throughout the state. And the map there shows the urban insets of St. Louis, Kansas City, St. Joseph, and some of our other urban areas as well. But we've been pretty successful in the last years reducing the number of poor condition bridges, and our asset management goal is to keep that number below 900. As you can see, the last couple years, it's kind of tapered off. We keep track of how many we add over the last 5 years to the poor condition and how many we remove from the poor condition bridges. And over the last 5 years, the average added was 94. That's up 1 from last year's total, and the average removed is 123. So that's down 1. So we're also at peak funding. We just had a 5-year phased-in fuel tax increase, and the last of that went into effect July 1 of this year. It was 2.5 cents a year over the last 5 years, so our fuel tax went from 17 cents a gallon to 29.5 cents a gallon. And so I guess my whole point here is to say we're getting diminishing returns on removing poor condition bridges with 10,427, and you're only taking 125 approximately a year of the poor condition bridges off the system. We're getting to a point where it's going to be more difficult. Our average age of the system is about 50 years. So I want to talk a little bit about the history of our design build law. It was first allowed in 2004 with Missouri State Statute section 227.107. And that gave us the ability to do 3 design build projects. I show you the icons there of the projects. The first one was the new I-64, and this was a 12-mile section of Interstate 64 in urban St. Louis. We ended up a complete rebuild of the urban interstate. We closed the road on 6 miles of urban interstate with over 120,000 vehicles a day, completely rebuilt it, rebuilt the overpasses and all that. And then the next year we closed the other 6 miles. And you would think closing a road that has 120,000 vehicles a day would be a major issue, and it was, but we had a great communication program. And actually some residents liked it because the interstate was closed right after the exit they used, and so there was no traffic on it, and so they said it saved them time. But anyhow, that was our first design build project. The next one was Casey Icon, and this was a cable stayed bridge over the Missouri River in Kansas City, carrying Interstate 29 and Interstate 35. The Safe and Sound project was our first bridge bundle, and this it started out as trying to repair 800 bridges. It ended up where we repaired 802, 248 of those we did design bid build, and 554 were led in a design build bridge bundle. And so that was our first bundle, and at 554 bridges, it was quite a deal. Throughout all the state, every county got a new Safe and Sound bridge, or redecked or repaired. So with the success of those 3 projects, the legislature expanded the use of design build in Missouri in 2012. And they limit it to 2% of the number of STIP projects per fiscal year. Well, we do about 400 projects a year, and so 2% of that would be, 8 projects. We typically don't do 8 design build projects a year. It's usually 2 to 3 that we let. So the legislature required us to pre-qualify or use a 2-phase procurement. So first off, we request for qualifications. So contractor, designer teams pair up and get together and submit their qualifications for the design build project. And after we receive all those qualifications, we review those. And if there are more than 5 contractor designer teams, we shortlist that to no more than 5. And at that point, we request for proposals. We have to have at least 2 design build teams to make this award. So the short list is anywhere from 2 to 5. But then we request for proposals. We have one-on-one meetings with the teams, and they're free to ask any questions on what do you think about this, or what is Missouri open to that. We also have approved alternate standards. It's basically where the contractor designer team can propose things that are happening in other states as standard, and we can look at them and say if that's acceptable or not. So if we look at our design build program over the last 21 years, we've had 31 awarded contracts worth over $4.7 billion. 9 of them are currently under contract and in procurement, worth over $2.5 billion. We've had 8 design build bridge bundles that improved over 700 bridges. And on the design build bridge bundles, typically we use a fixed price variable scope approach, and our people that are in charge of our design build programs say that helped us realize an additional 35 bridges improved over on the 8 design build bridge bundles. So what do we think of as the benefits of bridge bundling. And there's four things that really come to mind when we think about this. So as I just mentioned, most of these bridge bundles, we have a fixed budget. So we've got a certain amount of money that we can dedicate, and we give the design build teams more scope than they can complete with that. And so one of the things we get is maximize scope. And you'll see when I talk about the Farm Bridge program, how that worked out. We can also control the design costs. I suspect we have a lot of consultants on board, and for some reason, I hate to say this, but for some reason, I think the contractors can get a little more design effort out of the consultants than MoDOT, the state, in their negotiations, I guess. Promote innovation is a big thing, and this is where the Simple for Dead, Continuous for Live idea came up in the Farm Bridge program. Although I showed the icons of the other 8 or other 7 design build bridge bundles, there was different innovation that took place in each of these. For example, Safe and Sound, the contractor that won this, they set up their own letting system and subcontracted some of this work. We had on the Columbia I-70 bridges, the contractor chose to slide bridges in place, build them offline and slide them in place. The Farm Bridge program, as I said, used the Simple for Dead, Continuous for Live, which I'm going to explain as one of the innovations. They showed it, as Jason's going to talk to you later, as a approved alternate standard from another state. And then lastly, one of the benefits is it speeds delivery of the project, because often the contractor design team is given notice to proceed, and they've got a pretty good handle on where to start with their plans from their proposal, so they can get going as soon as they get notice to proceed and design progressing while the project is going on. Whereas if we did design bid build, you know, we have basically probably a year to 18 months of design phase before we produce letting plans, and then notice to proceed to the contractor. So it just speeds delivery of the project as well, which is useful in an inflationary market where the construction dollars are being eroded away by inflation. So let's talk about the Farm Bridge program. As I said, it's a catchy acronym for fixing access to rural Missouri. We identified 41 rural bridges in northern Missouri. And if you look at the map inset there on the bottom right, there are 41 red triangles there. One of them's all the way down there in the bottom of Warren County, kind of in the Missouri River Basin. But most of them that's in our northeast district, but most of them are up in the northern part of the state, most of them are north of Route 36 that crosses the state from Hannibal to St. Joseph. But we identified those bridges, those 41 rural bridges, based on 4 criteria. One, they were in poor condition, and as I showed you the map or the bar chart of our poor condition bridges, that's one of the things we're trying to do is reduce the number of poor condition. All of these 41 bridges were weight restricted. They were all 1-lane bridges on 2-way roads. So 1 lane but carry 2-way traffic, and also they were on timber piles. So if we look at a few of the representative structures there, over here in the top left, you can see poor deck condition, simply supported steel beams on timber beam caps and timber piles. Down here in the bottom left, deck condition poor, that it's got steel plates bridging over potholes or deteriorated deck. Top middle, underside of a deck that's had so much deck repair that they just left the formwork in place, and so poor condition. You can also see the timber beam cap there as well. I'm gonna do like Dr. Aziz Namini and try the laser pointer here. So timber beam cap, timber piles on the abutment there. As I mentioned, one of the criteria was 1-lane traffic for 2-lane road. So this is striped for 1 lane on a 2-way road. And you can see this one maybe has some sight distance issues with the curve there as well. So it'd be good to have that as a 2-lane bridge. And then this is just a general picture of another farm bridge program, timber piles, deteriorated deck, generally steel girder bridges. All right, so we had 3 teams that proposed on the farm bridge program. And as I said, there were 41 bridges that were available for selection. There was a limited amount of budget, so we knew that we weren't going to get all 41 of those replaced. We did have a grant from Federal Highway on this one, as I mentioned, and they gave us less money than we asked for because we did throw in all 41 bridges. So what we did work out with them was that those remaining bridges that were not replaced, we would get them in the STIP over the next 5 years. So the best value proposal was by Lehman Construction and Wilson and Company, and you'll hear from Jason from Wilson and Company later. But they chose to use the Simple for Dead, Continuous for Live concept, and they replaced 25 of the 31 structures with that Simple for Dead, Continuous for Live. 3 of them were single span bridges, and 3 of them were reinforced concrete box girders. The other teams, one other team proposed mostly pre-stressed concrete replacements, and the other one had a mix of steel and pre-stressed as well. What we did get with the Lehman Wilson proposal was low maintenance steel structures that allow for future redeck and rehabilitation. So that was good. Because they replaced 1 additional bridge, we got an extra 2,300 square feet of existing bridge deck replaced. They chose, of the 41 structures, they chose the routes that had the higher average ADT. So for the travelers in northern Missouri, they got the bridges that were more traveled with local traffic, and the highest average benefit cost ratio of any proposal. So what is Simple for Dead, Continuous for Live? We've already heard Dr. Aziz Amini talk a little bit about it, but for us, it's multi-span bridges using simple span wide flange beams made continuous like that other material. You know, we've been doing pre-stressed concrete beams, simple for dead, continuous for live, since I think the first one we built in Missouri was in 1961. So that technology has been widely used and well known. So here we have down there at the bottom, a general elevation of the farm bridge program. They were all 3-span bridges, 3-span structures. They all had a 24-foot wide roadway width. As I said, these are on rural roads. Maybe some states these would be considered county roads, but in Missouri we have a lot of what we call lettered routes, and they're the farm to market routes. So 24-foot wide roadway width is appropriate for 2 lanes, and generally wider than the roadway in many of these locations. Probably roadway's 22 feet wide. We use 4 beam lines. It's 7'2" spacing with 2'7" overhangs, and we use a type D concrete barrier, which is a 42-inch tall single slope concrete barrier. Concrete pile cap integral end vents were 3 foot by 4 foot. Concrete pile cap intermediate vents were 3.5 foot by 3 feet. We used end bearing and friction pile, and the average length per bridge was about 106 feet. So what is SDCL? Here you can see one of the farm bridge programs, the intermediate diaphragm there before it was cast with concrete. There was a question brought up earlier about skew. Notice that this bridge is skewed, but the ends of the beams are cut square, and the compression blocks that you see down there are cut square. Just 3x3 steel blocks that's shown over here in the detail. There are holes in the web at the intermediate vents as shown down here. section at the ends of beams at intermediate bends. That's for passing the skin reinforcement of the diaphragm through the beam web there. You see a shear key and some bars to connect all of this together. At the end bends, in order to prevent a little rotation to make integral, we had 3/4 inch studs welded to the web as well. So let's move on to the next slide. Here's a intermediate bent on a square structure, as you can see. And as Dr. Aziz Amini talked about, you pour about 2/3 of the diaphragm full of concrete so that you provide some restraint from twisting when you're casting the deck on the ends of these girders. You do that a little bit in advance. And also you'll notice in here, there's a plate that is intended to make the crack form at that plate, like Dr. Aziz Amini was talking about, of the crack forming there at the intermediate bends. And that's shown in the detail over here. And I think Jason will go into that a little more as well. So why would we use this, or why did this particular contractor designer team choose to use this? It eliminates the use of traditional field splices, and Dr. Aziz Amini kind of mentioned that as well. You don't have to have a crane holding up the girders while you're making a splice at the inflection point or something like that. These simple details make steel much more competitive. There are 3 levels of certified bridge fabricator, and to do these simple for dead, continuous for live, you only need the simple fabrication qualification. You don't need the intermediate or advanced. And as Gary Wish will talk to us a little later, you'll see it's pretty simple on how to fabricate these. If you look at the 2 little plan cutouts here on the right side of the screen, you'll notice that in the top section there we have W18s by 158 at 60 feet span, and the girder depth there is 19.7 inches, and the piece weighs less than 10,000 pounds. You go, well, W18 by 158, that's a pretty heavy section. You could probably done better with making a deeper section. But that's part of the advantage here as well. The smallest pre-stressed girder that we would probably use in this situation for a 60-foot span is the MoDOT Type 3 pre-stress. That's 39-inch deep girder, and of course you got the deck thickness on both of these designs as well. But that weighs about 24,000 pounds, so about 2.5 times the weight of the steel girder there. And as I said, maybe that's pretty heavy on the cross-sectional weight of that steel section, but what that does allow us to do is use a shallower superstructure with no grade raise. As I noted before, these farm bridge programs were in rural Missouri, rural northern Missouri. We didn't have a lot of money to buy right away, raise the grade and all that. So using these shallower steel sections allowed us to maintain hydraulic opening, perhaps increase it just a little bit because the end bends were typically put outside of the existing end bends, and not raise the grade, which was a huge benefit of this program. And then the lighter beam depths, as you'll hear later as well, the crane needed to set these in some instances was probably just a track hoe, and lifting them with the chains or rigging on the bucket of the track hoe because the beam weights are fairly light. So I'm going to go through quickly here the construction sequence of the simple for dead, continuous for live. Here the contractor was pretty innovative in using the old material from the existing bridge as a template. So here's a scrap piece of wide flange from the existing bridge that he cut out holes for the piles for the in-bent construction. You see they've got the excavation there. They laid this on the ground, and they're going to drive the piles through that through those 4 holes there. So here you see them. They've got a leveling pad at the in-bent. They're starting to form the back wall and abutment of this. All our piles are galvanized. We've been, for the last 15 years or so, we've been using galvanized, hot dip galvanized piles, and we try to make that go down to the scour depth. In this case, I think all the sticks were probably galvanized because I'm guessing rock was fairly close here, but in general, the top portions of our H piles have now been galvanized for the last 10 or 15 years. Here's a look at the intermediate bents. 6 piles, same, you notice they used the same technique there with the old scrap from the old bridge to make a template to drive the piles, form up the beam caps, and cast the beam caps there. They've got, if you look here in the foreground of the photo, at the indents, you'll see these channels welded to the pile, and that gives a little bit of tolerance. The simple for dead, continuous for live girders are just going to sit right on that channel there and then be fully encased in concrete. And these channels here give a little tolerance for the construction accuracy. Here you see the forms removed off of the intermediate bents, and they're getting ready to go to the next phase. You see a track hoe there in the background. Setting girders here, 4 girders, as I said, 7'2" girder spacing. Some simple channel diaphragms there. This is a different bridge. They're setting girders. They've got a bigger piece of equipment here. You see a very lightweight sling to lift these girders. And here's a different bridge with all the girders set. And as I mentioned before, and I'm showing the channel detail here, you can see the channel at the ends of the beams and the detail. It gives a little width on either side of the pile. So perhaps here you can see it's a little off, and so that allowed them a little flexibility. The studs here on the ends of the beams encase all of that in concrete. There are some holes here as well where they're going to run rebar through the front face of the diaphragm, and these are shown in all the details here, the little channel and so on. As I noted before, you cast a little bit of concrete in the ends and the intermediate bents, so that you provide some torsional restraint to the girder before you cast the deck. And here you see this indent is cast there up to the deck level. Here's the slab after it's cast, and you see they're putting curing compound on there. Missouri allows slip forming of the barrier curbs, and in many cases that is done by a DBE contractor. For many of our contractors, the slip forming the barrier curb is one of the activities that they do. Here's a completed bridge. It's a nice bridge there. You got the 42-inch single slope barrier. You'll notice slab drains at the edge of instead of the curb outlets on the old decks that I showed you, where the deck was all deteriorated at the curb outlets. These slab drains extend below the bottom of the girders. And these routes typically probably don't see a lot of salt, so they'll be good shape. So there's finished product. As I noted, slab drains extend below the girders. These girders were galvanized. Initially, I think they were proposed to be weathering steel or painted girders, and I think Gary is going to talk about that a little bit, but there were some supply issues when this happened with the paint, and so the contractor design team proposed doing hot dip galvanized. These are short enough sections that you can usually do a single dip on all of them. The tanks around here in Missouri, we've got tanks that are over 50 feet long. So we've got galvanized girders, a jointless bridge. These things are going to last a long time because they're not going to get heavy salting in the winter because of the route status. But you see, they're nice looking bridges that are going to last a long time. There's a spray coop going over one of them. It looks like it's a narrow bridge, but it is 24 foot wide. But when you have an implement that big, it takes up quite a bit of the deck width there. So nice bridges. And like I said, will last a long time. One of the things that you might be thinking about with such shallow girders is how do you form up the overhang without twisting the exterior girders? And that's part of the reason why you got to cast the diaphragms first and all. But if you use conventional brackets, cantilever brackets, you see there's a very significant horizontal component to the load of the machine, the deck casting machine, and the cantilever weight itself. So you either got to do a lot of blocking in there to prevent twisting, or you can use a needle beam type of situation where you're essentially supporting the overhang with a beam that is attached to the exterior girder, basically hanging down from the exterior girder and pushing up on the next interior girder. And so they did this needle beam type system on some of the farm bridge program bridges. So since that farm bridge program, we have allowed the Simple for Dead continuous to live on other projects. So the Northwest Bridge Bundle was followed up after the Farm Bridge program was completed. This is underway. 2 years of 3 is already complete. And the Northwest Bridge Bundle had 9 Simple for Dead continuous for live superstructure replacements and 15 Simple for Dead continuous for live full bridge replacement. So I'm showing here bridge number N0714, which is not important to you, but it's in Sheraton County. It's up there in Northwest. It was, as you can see over here in the bottom left, we call these U-beams or deck girders. They were, we had a number of these built in the 60s. And they were built with lightweight concrete as well, so about 120 pounds per cubic feet concrete. And you can see it's just a bunch of U-beam bridges. Sometimes they're called bathtub bridges, but basically you take a bathtub and flip it over, and then you bolt them together. But this is what the state of them looks like now, 50 years into their service life when they were designed for a 25-year life. So this one got a superstructure replacement in the Northwest Bridge Bundle. And here, like I said, you can see the profile on the underside. Here's the superstructure replacement with SDCL, nice galvanized beams, slab drains, and you can see the underside, similar views there. And they used some of the slab and other new riprap to armor the bank there. So we're doing this more. This was, see 24 more SDCLs. And in addition to doing design build projects, we're doing 14, or we have 14 Simple for Dead continuous for live replacements and 1 superstructure replacement by design bid build since September of 2023. This is a bridge in Atchison County, which is up in Northwest Missouri, kind of near Nebraska. You can see this one's a little bit more significant, big web walls to prevent drift from hanging up in the intermediate vents, and the girders are a little deeper. We allow the use of stay in place form, as you can see here, but super nice looking galvanized beams. Here's galvanized pipe piles as well. This is all drain route K, which is pretty much in central Missouri. So to summarize, we've did 40 SDCL replacements and 9 SDCL superstructure replacements by design build, 14 replacements and 1 superstructure replacement by design bid build since September 2023. And we have 2 more SDCL replacements and future letting. So this is a total of 66 bridges that are completed or in progress. With that, I would entertain any questions. There's my contact information if you'd want to call or chat or email about our experience with SDCL. We'd be happy to do that.
Okay, Brian, this is Paul Isles. The first one was, person was especially interested in retrofitting existing simple span steel beams, steel bridges. Do you see SDCL, the concept being applicable for retrofits?
So that's a great question, Paul. And actually, we have done this on a couple instances where we've had one of them. We got federal money with the state. What do they call it? It's a federal highway program, STIC. I don't remember what the acronym stands for, but it's basically research concepts. And they were talking about using ultra high performance concrete for doing this exact thing, making simple bridges, simple span steel bridges continuous. And somebody brought up the question about link slab earlier. They also throw that into that stick program. But we got a little bit of funding to try this on a bridge. You know, a lot of these simple span steel bridges that were made in the 50s and 60s, as somebody alluded to about Ed Wasserman and the joint there, the ends of the steel beams get all corroded and you lose section loss and so on. And we've had several where we've done rehab projects on simple steel bridges where we've made them continuous. One, we got funding from a special federal highway program to use ultra high performance concrete. And then another, we just had our own bridge crews do this because we had to close the interstate and truck traffic was going on a numbered route and kind of crushed some webs. So we closed that bridge and had our own crews do this simple for dead, continuous for live. Not as a design feature or anything like that, just to get it by. That bridge has since been replaced. It lasted about 2 more years after that. It was in the STIP, but that's a great question. And yes, we have done that, and I can see where it would be applicable to rehab, especially deteriorated ends of simple span beams that, you know, section loss and so on has caused the condition to be worsened.
Okay, we have one more question. For the Missouri DOT rural projects, are the bridge lengths set at 1.25 times the bank full width over water?
I suspect Jason can help out on that, but they were typically slightly longer than the existing bridge just to avoid existing foundations and all. The hydraulic situation was improved in all cases. On now our bridge bundles, our owner's consultant typically provides existing hydraulic models, and the proposers use those existing models to put their proposed model in. I don't know the exact specifics of the span arrangements or bank width or anything like that. Maybe Jason, I hate to pawn off the question, but maybe Jason can address those as well. Or if you want to bring that up again when Jason's done talking. So.
Okay. All right, Kathy, so I'm going to turn it over to you.
Great. Thank you, Paul, and thank you, Brian.